Good morning, everyone. Welcome to Organic Chemistry. In this short video, I would like to give you an overview about two main topics, stereochemistry and some reaction mechanisms, such as SN1, SN2, E1, and E2, and a little bit of introductions about alkenes, okay, just the naming and physical properties. Okay, first of all, stereochemistry is a branch of chemistry that emphasizes on chirality of molecules. Talking about chirality of the molecules, we're talking about the handedness of the molecules. Okay, if you take your right shoe and left shoe, you put them together, they will be mirror image to each other, but they're not the same. The right shoe will not fit the left foot. Okay. In other words, we can say shoes are chirals. Okay. And the pair of shoe, the left one and the right one, are enantiomers to each other. They're mirror image to each other, but they're not the same. They're not superimposable. Okay. Well, molecules are the same way. When you have a molecule and you build the mirror image of that, and if they're not the same, then they make up a pair of enantiomers, and each of them is called a chiral molecules. Okay, so that's the definitions. The definition is enantiomers are non-superimposable molecules that are mirror images of each other. Okay, so that's definitions. Now, if we use that definition to recognize the chiral molecules, it's a little bit difficult sometimes. Okay, so especially the one that has more than one chiral carbons. Okay, so and here's the quick way. Okay, first, whenever you got a molecule, if it has only one chiral carbon, then the molecules is chiral. Okay, for example, let me show you guys this. Okay, for example, I build a few molecules here. The first one, for example, which is chiral. Okay, so you look at the molecules. First, you look at the carbon. It looks like this one has only one chiral carbons, at the most. Okay, so you look at the carbon and you take a look at four substituents that bond to that carbons. The first one is hydrogens. The second one is chlorine or chlorol, and you see a methyl. Oh, but you got another methyl. Okay, so the rule is if you have two identical, then that carbon is not chiral. That means that molecule is not chiral. Okay, and you look at the next one when you see a hydrogens, chlorine, Br, and a methyl. So that's four different things. Okay, four different substituents. So that carbon is chiral. Okay, now if you look around, there's no other chiral carbon because that carbon has three hydrogens, so that's the same, right? So that cannot be chiral. It doesn't have to be carbon. It can be any kinds of atoms as long as it has four different substituents. It is chiral. Okay, but for this, we focus on the carbon. So that's chiral because it has four different substituents. If a molecule has only one chiral carbon, the molecule is chiral. Okay. However, if it has more than one, if it has especially even number of chiral carbons, it might or might not be. Okay, so let me show you the next example. The next example is here on the practice exam question set. We're looking at this question: which molecule is achiral, which is not chiral, right? Okay. Now this one is pretty tricky. Okay, so the first one here. Okay, the first one here. You're looking at that carbon. It has four different substituents. It has hydrogen, Br, Cl, and this carbon with a lot of stuff. So that's four different substituents. So that carbon is chiral. And if you look at this one, it's also chiral. Okay, so you got two chiral carbon here. So what's going on, right? it's the overall molecule's chiral. You know, if you remember the polarity stuff, when you have one bond is polar, the molecule is polar. But what if you have two bonds, two polar bonds in the molecules? Then you ask yourself, do they cancel out, right? Same idea here, okay? If the polarity cancel out, then the molecule is non-polar. Here, if the rotation cancel out, then the molecule is achiral. Okay, so what is rotations? Okay, now we look at this. First, we prioritize by atomic numbers, and here I have the same molecules. I just redraw them with the label. Okay, so I label bromine is number 1, Cl is number 2, and that carbon is number 3. Okay, bromine has atomic number 35. That's why it's number 1. It's the highest. 17 for Cl, and then that's a carbon. That's 6. Even though it has a lot of stuff, but it's still a carbon. So that's 6. So 1, 2, and 3, and hydrogen is 1. 4, atomic number 1. So that's the lowest, right? And that's the reference. And remember, it has to be away from the viewer, you. Okay, so now you're rotating 1, 2, 3. That's counterclockwise. That's why it's S. And hydrogen's away from you. Okay, now you're looking at this one. It's the same idea, except Br is 1. Okay, Cl is 2. And then that's 3, right? So you go 1, 2, 3. Look like you're doing counterclockwise. Okay, it is counterclockwise, but remember hydrogen is towards you, so everything you see here is opposite. So it look like S, it's actually R. Okay, so 1, 2, 3. Okay, there it is. 1, 2, 3. So it look like going to S, which is actually R, because hydrogen is towards you. Okay, because you got to turn the molecule, you got to turn it around. Okay, all right, so now we got the carbon on the top here is S, the bottom one is R. Okay, now this is very important. You got to examine the quality of the substituents. The first carbon here is S. It's got a Cl, Br, and a hydrogen. Okay, this one's the same thing. It's got a Cl, Br, and a hydrogen. So these two guys have the same kinds of substituents. Same exact. They're only opposite in the spin. Okay, in one is spin S and one is the R. Okay, so therefore they cancel out. I mean, you can think about it that way. Okay, the molecule has internal plane of symmetry, but that's kind of difficult to see here in this case based on the drawing. If you do the right rotation, you'll see it. Okay, but I think the easiest way is to say same substituents, only opposite rotations. They must cancel out. Okay, when they cancel out, this one is achiral. Overall, there's no net rotations. Okay, and this compound is also known as meso compound, MESO. All right, so that's the reason why. Okay. Okay, so that's achiral. That's why the choice is A. Now this one right here is which, you see. So Br is 1, 2, and 3. So it rotate counterclockwise, but it's actually R because hydrogen is towards you, the viewer. So remember, if hydrogen is towards you, everything you see is exactly the opposite. Okay, so this one look like S, but it's actually R on the top. And then the bottom, the same way. Okay, 1, 2 is S, but it's actually R. Okay, so it's RR. So the molecule RR, they don't cancel out. Okay, so R, they don't cancel out. They actually add up to the rotation, if you can think about it that way. Okay, only RS will cancel out. Okay, only have to be opposite spin. So that molecule is chiral. And then you look at this molecule, it's also chiral because, you know, this 1, 2, 3. Okay, so that's S. Hydrogen's away from you, so that's the way it is. Okay, that's S. Okay, So that's S. Now this one right here, the second one, we don't have to worry about because it's got two bromine. If you get two bromine, that carbon is achiral. So that means this molecule has only one chiral carbon. Therefore, it's automatically chiral. Okay, so 3 is chiral. This is chiral because it's RR. And this one has only one chiral carbon. So both 2 and 3 are chiral. Leaving the first one is achiral because of the cancellations. Okay, so with this example, we pretty much learn everything, how to recognize the chiral molecules. Okay, and back to the first one here, cis and trans isomers are, they're cis and trans, so they're not mirror image because, one is cis and one is trans. And later on, we'll have an example like that, okay? I think I'm going to scroll it all the way down when I see an example like that. I don't see, okay, but cis and trans, you know what I'm talking about, okay? Cis and trans, like a cyclic, like a ring structure with 2 groups on the same side, that's a cis, and then you got another structure like a ring structure like cyclopentane with 2 chloro on opposite side, that's a trans. Okay, so they're not mirror images to each other, they're not superimposable either, so they don't really fall into enantiomer category. So we call them diastereomers, and diastereomers are also stereoisomers. That's why the answer is E, more than one of these. Okay, above are correct. Okay, so so that's stereochemistry. It's pretty cool how to recognize them, and here's a good one. The way to know these two guys are identical or enantiomers or not by assigning. Okay, you assign the stereo, the chirality, the R or S. And this molecule has 2 chiral carbon. I can see here this first one right here has a methyl, the chloro, and a carbon with complicated stuff on it. Okay, now it doesn't show you the hydrogen, but if it show you this carbon has the remember, carbon has 4 bonds. It has the Cl going away from you. That means it has the hydrogen towards you. Okay, so that's what we got to understand. Okay, hydrogen towards you. And this one right here, it's got a methyl that's towards you. So the hydrogen, it has a hidden hydrogen there that's away from you. Okay, so if you assign R or S for each of them, then you can tell they are identical or opposite. Okay, opposite spin means enantiomers. If they have the same spin, same quality of substituents, atoms and everything, then they're the same. Okay, opposite spin means enantiomers. Okay, so that's good for that. So we need to move on to other interesting topics such as substitution and eliminations. Remember, substitutions is there's 2 different kinds. First is SN2. In substitution SN2, the first requirement is the SN2 means bimolecular. So you have 2 molecules involved at the same time. That's what it means, bimolecular. That means your rate depends on both of them. Okay, but first of all, you need your RBR, which is the alkyl halide, to be either primary or secondary the most. You don't want a tertiary for SN2. And you want the nucleophile to be a strong nucleophile, like we discussed in the class. OH minus is a strong nucleophile. OCH3 minus is also a strong nucleophile. Okay, and with that, if you don't see OH minus, you just see water or alcohol, then you don't have a strong nucleophile. Then it's not going to be SN2. Okay, and that's how I would recognize them. So you got a alkyl halide and you got a strong nucleophile. This is an SN2 reaction because you see the Br is substituted by OH, and X minus it means Br minus. Okay, Br minus get kicked out. So that's why the rate here is bimolecular. So you have two of them involved, okay? And you can tell by substitution because Br is substituted by OH. So there's a lot of detail. You have to look at the product to see if it's a substitution or eliminations. Remember, elimination give you alkenes, okay? Assuming you start out with saturated alkyl halide, your product will be alkene, okay? That's elimination products. Okay, so that's a good one. That's a good substitution reaction. Here's another substitution reaction, but this one tells you exactly what it is. You have an iodide right there, and this is secondary, so it's acceptable for an SN2 reactions. You have a moderate nucleophile. Anything minus, don't worry about the sodium, that's a counter ion. Anything with the minus, this one is this, okay? Anything with minus is a decent nucleophile. And you can see the product. It shows us here the product. So look like iodide is kicked out, and then you got the acetate ion replacing the iodide. So that's replacing mean substitutions, okay? And that's a substitution, and it tells us it's SN2. So when you double the rate here, it's saying that when you double the concentration of the first reactant and the nucleophile, this is known as the substrate and the nucleophile. If you double both, you remember the rate depends on both of them, second order. So if you double both of them, that's 2 times 2. So the overall, you double the concentrations, then the overall rate should be 4 times, okay? Because double mean 2 times 2, and that's 4 times the rate, okay? So that's talking about the rate of SN2 reactions. Pretty good. The another thing about SN2 is when you when you start out with S, you get the products is R. And when you start out with R, you get a product is S. Similarly, when you start out with cis, you get trans. Start out with trans, you get cis. Okay, this is a good example here. If you do S and R, it works the same way. This is a substitution reactions. Okay, very similar to the previous one. From the product, we from all the choices here, okay, all the choices here, the this one from the previous example, this is an acetate, so it's not strong enough to be a base, okay? So this one is really on the borderline, but it's not strong enough to be the base. A base is more like sodium hydroxide, sodium OCH3, which is sodium methoxide, okay? Now, if you do the elimination to make a double bond, that's difficult, okay? So substitution is more likely the case here, and that's a decent nucleophile, okay? So it's going to substitute. So now the question is, you have this methyl and iodide on the same side, and that's a cis. So when you substitute, okay, that has to be opposite. Okay, if you remember, you have your R, you get the S product. You have cis, you get the product is the opposite, which is trans. Okay, and if you do rotation, you get that too. Okay, so when you substitute, it has to be opposite. That's why it cannot be the same stereochemistry. It has to be opposite. It cannot be this one. It cannot be that one either. These two are the same actually. So it has to be opposite, which is trans. Okay, and you, if you think about mechanism, this will come in from the back side, and then iodide will leave from the front side. Okay, you can think about that way. If you assign R and S, I would go. This would be, just for fun, this one right here should be 1, 2, and 3. That should be S, and the hydrogen's away from you, so that's S. And this one right here is R, because hydrogen's towards you. Okay, so it looked like S, it's actually R. So you start out with S, your product is R. Okay, so it's the same way, but it's much easier to see. You start out with cis, you end up with trans, and that's the nature of SN2 reactions. The stereochemistry always get reversed. Okay, and here is another good example of SN2 reactions, and if you replace this, your product, you would replace the Cl by the Cn, but notice the Cl is sticking out. So when you draw the structure of the product, the Cn should be away from you, okay? Because it has to be opposite, okay? So hopefully you get the idea. And for chapter 7 is the first part of chapter 7 is just structure and naming of alkenes, and nomenclature of alkene, and that's the product of eliminations, such as this one here. This is a good example of eliminations. You start out with a primary alkyl halide, and your product is an alkene, so you automatically know it's eliminations. But now the question is it E1 or E2, right? Remember, E1, you need a cation intermediate, so it cannot be primary because primary cation is not stable. You have to have at least a secondary. Okay, so this is primary, so it has to be E2. It has to be D right here, E2. Okay, why? Because it's primary. That's the reason why. If it's a secondary or tertiary for sure it's going to be E1. Okay, and then you need more information. If it's a secondary, you need like the nucleophile, the base. In this case, you need a base. Okay, if it's a strong base, it's E2. If there's no strong base present, then it's E1. All right, so hopefully that will be helpful to overview the stereochemistry and substitution and eliminations. All right, thank you for watching.